Hey, what's up, guys? Yeah, so today, I want to introduce the Euler summation formula. So this formula is very, very good and approximate the analytic number theory, or basically approximate the integral, which is very, very commonly used in the analytic number theory. Okay, so let me just write down theorem. So for this, and let's say f of t is a real number, a real function. Let's say defined on y-axis. Then, so our goal is to approximate the summation into the integral. Okay. So usually you will think that the summation approximate integral is very easy, right? Just by definition, use the Riemann integral, right? But we need to find its error term, right? So right, this is n greater than y and that's equal to x is basically as a x y f of t dt. This is the integration part, and plus this is x, y is a small t f prime of t. Although, so we should mention that f prime should be continuous, so that you can do integral, and that is bracket x f of x plus this bracket y f of y. Okay, so this notation denote the fractional part. So basically t minus t. Okay, so this is called the fractional part. So for example, 5.1 will be 0.1. 1.2 will be 1. Sorry, 0.2. Okay, and the integer will be 0. Okay, so this is called a fractional part. Okay, so this integral is commonly used. Okay, so basically, you can so once you understand your f of n, then you can use this theorem to bound it to get your integral, and these three terms are real terms. Okay. Okay, proof. Proof is I should say proof by yourself. Okay. Sorry, just for kidding. Okay, but I think the proof is very trivial, so you should try to prove it. Okay, so let me just write down. So let's write f of x in terms of this x and the x minus this. Okay, so this is the integral, the integer integer part of x, and then you write this, and right, let's do this, right? So hopefully you can see this guy is basically x y f of t and df of t. Okay. Hopefully you can see this. Okay, so right, this is definition. There is a little bit technical to how to write this term, right? So let's see. Let's just write this x y f of t. But because I take this, right, so it becomes dx minus d this. Okay. Sorry, I should use t. Okay. Okay, so now I got these two terms. Okay, so the first term is this. This is what I want, and the second term that x y f of t d this, I can use the integration by part. Okay, so I use integration by part. So I get I get what? I get f of t minus by these terms minus this is x and y, and then minus the derivative t dt. Okay. Okay, so you can spend it. You can just spend it out, then you get the answer. Okay. So example. So now we have this power tool, right? We can do something non-trivial. Okay, so the first example is partial sum of harmonic function, harmonic series. And by the way, this is, I think I already proved in my previous in my old videos that there's a called Euler-Maclaurin constant. So basically, in my previous video or not, I have proved this. Basically, if you sum over I from 1 to n and take log n, and then you take this n to be infinity, then you can prove it converge. Okay, so our goal is to bound this guy, right? We want to bound this. So the results will be log x plus gamma plus O, big O, 1 over x. Okay, so this is what we gonna to do using the Euler summation formula. Okay, so proof. Okay, so remember our let's try to do this. Okay, so very simple, right? So you should take f of n to be 1 over n, and then take this guy. Okay, so in our case, that y should choose to be what? To be 1, right? Okay. So using the Euler summation formula, you get dt plus x1 t derivative dt plus x1 x plus 1. Okay, so this is the Euler summation. And we don't care about these two, right? Because these two are constant, right? And these two is log x. So I can write log x minus I of x plus 1 plus O 1 over this, right? This 1 over this come from this, right? Because you get 1 over t and you can prove this. Okay, and that is I of x. Sorry, let me see what's going on. Okay, so yeah, forget about this O 1 over x. Let's imagine. So this O 1 over x can bound this. Let's see, right? So this is can bound by this term, right? Because this is at most. Right, this is the fractional part, right? So yeah, so when x is large, you get bounded by O1 over x, and let me just define I of x to be x1 bracket t squared dt. Oh, so to bound these terms, let's do this, right? So this your I of x can be written as a 1, let's say I, so some finite constant to the tail, right? So let's do the infinite tail. So this is constant. And it's just 1 plus big O infinity x 1 over t squared dt. Okay, so this is just a constant plus O 1 over x. Okay, then you can check this constant can be written as Euler-Maclaurin. Okay, and yeah, there are other examples that but probably it's not important. Yeah, so I think another example that is that you can prove this. C is a constant. Okay, so you can do the same thing to prove it. Okay, so I think I don't want to prove, but you can check it. And yeah, and also so one can prove this is corollary of, let's say you take log n, and right, you take basically x log x minus 1, and then you just bound this. Okay, so yeah, so this is also can easily prove, right? Because you just take this and it become x, right? So this is half is bounded by this big O. Okay, so I think that's it. And yeah, next time let me just maybe talk about the integral representation of Riemann zeta, but I think maybe it's not important. Okay, that's it. Yeah.